Hello Math 2413 students, welcome to Calculus. Here's Lesson 1, Vectors and Vector Functions. This is a fallout topic from Pre-Calculus, Math 2312 according to Texas Common Core numbering system. The real calculus material begins from Lesson 2. Now this is from Pre-Calculus, so there may be some students who are familiar with all these. Well, please be patient in that case, good for you. But there must be some students who are not so familiar with any of those. For those students, let's begin all the way from the starting point. Vectors. What is a vector? The term vector is used by scientists to indicate the quantity that has both the magnitude and direction. So, magnitude and direction, those are two critical aspects. But this is a math course, so we need some more. We want to do some mathematics with those, so we need some algebraic rules as well. Let's talk about those one at a time. Here's a visualization of the magnitude. You can see two different vectors, v1 and v2, colored in blue and red, but they share the same magnitude, visualized as the length of the arrow. We use the absolute value notation to represent the magnitude. Now this time, direction. Two different vectors, v1 and v2, but they share the same direction. Two different lengths, two different magnitude, but point toward the same direction. And we use this hat notation to represent the direction vector. Okay, so much for the magnitude and the direction. Now, let's do some more mathematics. This is a math course, so let's do some algebra. We can consider this algebraic operation with vectors. The vector addition. It can be visualized either by number 1 through a parallelogram or number 2 through a triangle. Either way, we get the same thing. Suppose that we have some weight here at the black point, and then a group of people are pulling it in this direction, and then another group are pulling this way to red. And then the net effect is this purple force. That's one way to see a vector addition, through a force model. Now look at this, starting from the same starting point here, and let's move it to this point, following the blue vector, and then move it again, following the red vector to the final place. So what's the net motion? Start from here, and then end it over here. So you can visualize the vector addition through the displacement. Force model or displacement model. Either way, it's the same thing, because they're all based upon the same parallelogram, as you can see. That's for vector addition, and another operation that you have to know is a scalar multiplication. Now, what is a scalar? A scalar is a quantity that has only the magnitude, no direction, just magnitude. Here, you're looking at a scalar multiplication by a scalar 1.88 something. So this purple vector is nearly twice as long as the original blue vector, because we multiply by k, which is almost 2. Now this program is randomized, so let's run it again for a different k value. This time I got negative 0.6 something. Good, we got negative right away. So this purple vector is about 64% of the blue vector, but the opposite direction because k is negative. This kind of thing is a scalar multiplication. So these are two standard vector operations, or algebraic operations of vectors rather. And there's some other operations to consider as well, but those are case by cases and they are not applicable to all vectors. These three, they apply to all vectors in any case. Interestingly, the starting point does not matter, at least at our level. Here's a visualization. You're looking at a bunch of vectors in different colors, but they're all the same. Same magnitude, same direction. They do not depend upon where they start. This kind of vectors are called free vectors. And in 1011 math course, well, I'd rather say in undergraduate math level, we consider only the free vectors. There are the kind of vectors that depend upon the starting point, but those kind of vectors are a little bit different. We usually call it tangent vectors, and those are different. Of course, a bit harder. And if you went through some vector quantities already in physics or engineering associated to rotation and things like those, you must have seen that the starting points are playing a significant role. That's because the vectors you studied over there in physics classes are not free vectors, those are tangent vectors. Those are a little bit different, but we don't deal with tangent vectors in detail in undergraduate level. So let's stick to free vectors here. Okay, those are associated to the definition of vector quantity. And let's consider some more aspects associated to viewpoints. Same vector, but depending upon which reference frame, which coordinate you're looking at, may be represented a little bit differently. If you place it on a plane, then you have only two coordinates or two components. Now, if you place that in 3D space, then you're going to need three components, three coordinates or three components. You can consider n-dimensional space as well, but that's a bit too much. After all, this is an undergraduate level course. Excuse me. We consider n-dimensional in undergraduate level mathematics too, but not in calculus level. Anyway, please remember these terms. Depending upon where we put the vectors, they could be the same vector, same arrow, but depending upon how to set up our coordinate space, it can be viewed as one-dimensional, two-dimensional, or three-dimensional, and so on. Now, if you have multiple vectors, then of course, bigger dimension will probably be necessary. One last thing. According to our textbook, we use these triangular brackets to represent the coordinates and components of vectors, but that's not a usual notation. Universally accepted notation usually is parenthesis expression, but our textbook author doesn't do it that way, and I'd better not cause any confusion, so I'll try to follow this triangular bracket notation whenever possible, but please be warned, our textbook author sometimes mishandles it, I think. I don't think it's intentional. There's some conflicts here and there, and I had a bit hard time reconciling those. I'll tell you what that point is. It's coming right up. Among those vectors, a particularly important type of vector is a position vector. Visualize kind of like this. Whenever you have a point on a plane, or if it is in higher dimensional space, it could be x, y, z, whatever. And let's suppose that you're sitting on the origin. If you point toward that, that's a vector. And that kind of vector is called a position vector. So the position vector is associated to a point. So what's the difference between a point and a position vector? Nothing. Absolutely none. So it is actually better to use parentheses and use triangular brackets once and then parentheses for another for the same point. Oh, that's too confusing, too conflicting. So I'll try not to do that. So for position vectors, I'll try to use parentheses all the time. I cannot promise because there are some conflicts in our own textbook, but I'll try to follow that so that you don't get confused. Now for other kind of vectors, I'll follow our textbook and use triangular bracket. And one such example is the displacement. Starting from here, A to B. So from A to B, what's the motion? Horizontal motion, difference of x coordinate, x2 minus x1, that much I moved to the right. And then vertical component, y2 minus y1, the difference of y coordinate, that much I went up. Here, y2 minus y1 is negative, so the net effect is going up by -1, which is going down. So, see the difference in notation? For position vector, I'll try to use parentheses because there should be no distinction between a vector and a point. For other vectors, I'll try to follow our textbook's notation. So here's a summary. And then, if those x and y values, or a and b values, change by a certain variable, let's say t, which is typically the time variable, then we end up with a vector function. And if it's a position vector function, I'm going to use parentheses most of the time. For other vector functions, I'll use triangular bracket, as our textbook author does. A little bit confusing, sorry about that. That's probably why the majority of the mathematical world use parentheses all the time and never use this triangular bracket for this. But if I do that, then probably that's going to cause even more confusion. So I'll try to follow the textbook. Okay, we went through the definition and some properties associated to components and expressions. Let's see, we have sufficient time to do one more, I guess. Let's talk about the magnitude. And this is a magnitude formula. Does it look familiar? It should. Here's a visualization, and what is this? It's just a Pythagorean. X direction, y direction. So x squared, horizontal squared, plus y squared, vertical squared, is going to be the square of the diagonal. And then if you have 3D, then you're going to have plus z squared as well, but this is calculus 1, so let's stick to 2-dimension. By the way, for general case, if you have displacement vector like this, then you get a little bit more general, like this. But again, everything is just Pythagorean. So that's how you calculate the magnitude. Enough time for one more? Okay, all right. Vector addition and scalar multiplication through components. It's easy. You can just add up the x coordinates and y coordinates. Scalar multiplication, equally as easy. Just multiply by the same scalar for each component. And if you have 3D vector, 4D vector, 1,000-dimensional vector, no difference. Just do the same thing component by component. You want to see a reason? Well, here's a visualization. Oh, well, this is previous visualization, this one. So, horizontally, this blue x, same as this x here, this blue triangle and that blue triangle, those are congruent. So this blue and then this red, x1 plus x2, will get you to the end. Or y1, excuse me, x2, and then plus x1, either way is the same. And then vertically, y1 plus y2. So that's the justification. As for the scalar multiplication, yeah, okay, scalar multiplication. What can I say? It's just a similar triangle. This right triangle versus bigger right triangle, similar right triangle. So multiply the same constant k to all the sides. In the end, we get these conclusions. Let's stop here and let's discuss the next section, or next subsection rather, in a separate video. Stay tuned. I'll be back soon.